The numbers 1 through 20 are in a bag, and we're going to find the probability of drawing something from A intersect C. So if you look at what A intersect C is, it's 16, 18, and 20. So there's 3 elements in A intersect C. So the probability of drawing a tile from A intersect C is 3 out of 20 because there are 3 things in A intersect C and 20 total tiles in the bag. For J, it's the probability of A given C, which when you have this given sign, it means this is all we're looking at now. So instead of having 20 tiles in the bag, we only have C in the bag. So what does that mean is in the bag? This is all that is in our bag now, these 6 tiles. So what's the probability of drawing something from A if this is all you have in your bag? And there are 3 things, 16, 18, and 20 are the 3 things in here that are from A. So the probability of A given C would be 3 out of these 6. So 3 out of 6 or 1/2. Make a Venn diagram to wrap your head around all the numbers in this one. And it should look something like this. 55% order both. A total of 85% order donuts. So you need to put a 30 there, so the whole thing adds up to 85. A total of 60% order coffee, so put a 05 there to make the whole circle add up to 60. And then the question asked, what's the probability that a customer orders a donut or a cup of coffee? So we just want to know the probability that someone orders donut or coffee, that they're anywhere in these circles. And so add up all the numbers and it would equal 90%. So 90% of people are in these circles and order a donut or coffee. And I guess to finish the Venn diagram, I should say 10% of people don't order a donut or coffee. They're outside. So there are 53 total people. The chances of getting it, you would select a teacher if you randomly select one of the people is, how many teachers are there? 14 out of the 53. The chances you get a person with internet is 20 out of the 53. And then C is more specific. The chances you get a student without internet, well, there are 25 students without internet. So it'd be 25 out of the 53. And then D and E have givens. So the chances you get a teacher if you're given a person with internet is selected. It means that we know for sure we select someone from this column. That's all we're looking at. We're not looking at the total 53 anymore. We're just looking at whatever it tells us after the given. So there's only 20 people to pick from. What's the chances of getting a teacher? It's 6 out of those 20. And for E, a person with internet is selected given a student. So if we're only looking at the students, there's 39 total people we're looking at. So the chances of getting someone with the internet, or sorry, without the internet, is 25 out of the 39. For number 8, the definition of independent means that when A happens, it does not affect the probability of B, and also vice versa. When B happens, it has no effect whatsoever on the probability of A. So just 2 events that are completely unrelated and don't affect each other if one happens or the other. So like if a meteorite hits Jupiter, it doesn't affect the chances of the Colts winning the Super Bowl. Those events are completely unrelated to each other. And what it's asking is, what's the probability of A going to B if we know B happens? If we're given that B occurred? Well, because they're independent, and the definition of that means that because B occurred, it doesn't change or affect the probability of A whatsoever. So we knew the probability of A was 21%, and the probability of A, now that B occurred, is still 21% because they're independent. So number 11, elect exactly 2 types of movies. So we want people who are in only 2 overlaps, or only in 2 circles at a time. So we take this 2 here, the 17, and the 8. Those people are in 2 circles at a time. They like exactly 2 types of movies. These people are left out because they like 3 types, and all of these people like just 1 type. For B here, liked horror or romance but not action. So we want someone who is in one of these two circles, but they're not in the action circle. So these people like horror or romance, so do these two, and so do these 10. And those three numbers, they also do not like action. So those would be the three numbers we add together to get 26. Liked at least one type of these movies. So that means they're somewhere in one of these circles because they liked at least one of them. The fast way is to just do 100 minus the 9 who don't like any of those types to get 91. But also you could add up all these numbers and they'll add up to 91. And then how many didn't like any of these types of movies? Those 9 people don't like any of those types of movies. For number 10, you're going to want to set up a tree diagram. So look at all the percentages here and then make a diagram that would look like this. So 20% use drugs, which means you have to infer 80% don't use drugs. And then it tells you the probability of testing correctly positive or correctly negative for all those cases. And if you multiply along the branches, so 0.20 times 0.78, you get 0.156, which that's the probability for any random person that they use drugs and would test positive. So the probability for any random person that they use drugs and test negative is 0.044, and so on with these as well. And so the question asked, find the probability that the athlete is not a drug user given that the test result is negative. So we know we're only going to be looking at people who had a test result of negative. So you have people who use the drug and tested negative, and you have people who don't use drugs and correctly test negative. So all together, if you add those two numbers together, you have 79.6% or 0.796. 0.796 are the people who test negative. So the problem wants to know what's the probability that they're not a drug user. So out of that total 0.796, the part of that was from non-drugs users was right here, 0.752. So you have 0.752 out of the total 0.796, and that gives you a probability of 0.945. On test 3 now, number 6, there are 10 computers and 2 have defects, which you take away from that means 8 of them are good without defect. And we're selecting 4. And it says, what's the probability that none of the sample will be defective? So you need to read from that what's the chances you select 0 defective and 4 good ones? So think about each group, defective and non-defective, and how many you're picking from each group. So 0 from the defective group and 4 from the good group. So there was 8 good ones, and you're going to pick 4, and here's all the ways you could do that. There's 2 defective ones, and you're picking 0. And then that's all the ways that you could pick 4 good ones. And when you multiply those 2 together on top, and your bottom should be the total number of ways you can pick 4 computers. So there's 10 total computers, and you're picking 4. How many total ways can you do that? And when you simplify all those down, you should get 1/3. Number 7 is kind of similar to 6, where in 6 we had defective and non-defective computers, and here we're looking at different groups from a deck of cards. So for A, it's that they are all red cards. So again, we're picking 4. So 4 out of the 52. So our bottom number is going to be the total number of possible ways to select 4 cards. So it would be, there's 52 total cards and we're choosing 4. And then what about that they are all red cards? I have it written out here. There's 26 red cards and we're choosing 4. And then what the rest of the stuff, there's 26 black cards and we're choosing 0. So think about the 2 groups you have, red and black. You're picking 4 from this group, 4 out of the 26, and you're picking 0 from this group. And notice the pattern continues here. It was asking what's the probability you get exactly 1 club. So think of your 2 groups. You have clubs and then everything else. So from your clubs, there's 13 of them, you're picking exactly 1, and from everything else, there's 39 of them, and you'd be picking 3. And again, there's this many total possibilities of 4 cards, so that goes on bottom. And last one, so there's at least one club. The fast way to do that is to look at the opposite here. It says there's 13 clubs, I'm picking 0, and from all the other cards I'm going to pick 4. So this is the probability that you get no clubs. And so to get at least one club, you would do 1 minus that answer, because let's say this comes out to 10%. Let's say 10% of the time you get no clubs. Well, then that would mean 90% of the time you have at least one club. So whatever this comes out to, do 1 minus that to get at least one club. And for number 10, they tell us the probability of A, B in the union. Here's what they're asking for, but first let's make a Venn diagram, which we really want to know the intersection to make our Venn diagram. So remember the union rule, where the probability of the union is you're going to add the two parts together, the chances of A plus the chances of B, and then subtract the stuff that got double counted, which the stuff in the intersection gets counted for A and B. So you need to subtract the double count. So if you solve this for the intersection, it has to be 20%. So to make a Venn diagram, you put 20% in the middle, all of A adds up to 25, all of B adds up to 30. So that's what our Venn diagram would look like. And then let's look back at the problem. What's the probability of A given B? So the probability of A is 25%, and we knew that from the beginning. It told us A was 25%. But what's the chances that we're in the A circle if we know we're in the B circle, if we're given we're in the B circle? So instead of looking at the whole Venn diagram, just look at the B circle. So what you have here is a total of 30% of the time. B happens 30% of the time. And what portion of that 30% is actually in the A circle? And if you look at it from our diagram, that 20% was in the overlap, so it's in B and also in A. So out of the 30%, you have a 20 out of the 30 as your chances of being in A if you're given, if you know that you're in the B circle. So that reduces down to 2/3.